Okay, it's almost, it's exactly time to start. And I was away for 5 minutes from the screen, and a slide that wasn't supposed to be displayed yet had interrupted. Well, no big harm. Let's maybe sound check. The people who are watching live, can you tell me how the audio is? Should it be a bit louder, not so loud? I see there are several people watching live, so there should be somebody who can sound check. If you don't hear anything, that would be certainly good to know. Theo tells that the sound quality is okay. Good. Then we proceed that way. So the technical check, the video is obviously working, the audio we have checked, the recording light is on, the streaming is guaranteed by YouTube. We can start. This is the feedback webinar about an important week in the course, the week in which the general framework in which hyperfine interactions fit is presented. And let's see what you did about this and which feedback I can give on this. The first and most important part of the week was this very important picture number 1, which several people liked. And here you have it. This is the picture that summarizes the entire framework of hyperfine interactions, with the large energy distances at the very left, nuclear levels, and at the very right, the hyperfine levels, which are due to the shape of the nucleus in various meanings of the word: electrical shape and magnetic shape. And to draw your attention to the different scales that are in this picture, scales that are not shown correctly, the picture is not to scale. In order to draw your attention to that, I asked you if the arrow, the nuclear arrow if the hyperfine arrow at the very right would be 5 millimeters long, how long would the nuclear arrow at the very left be? And so the answer to that was, if you put a ruler next to the hyperfine lines and you see these are 5 millimeter apart on this picture, then the nuclear levels should be 5,000 to 5 million kilometers apart from each other. 5,000 kilometers, that's roughly the radius of the Earth. 5 million kilometers, that is 10 times the distance between the Earth and the Moon. So the word hyper in hyperfine is not an exaggeration. Compared to all the other energy levels in this scheme, these are very, very small energy splittings. And if you understood this, then you can answer confidently to this statement that you can list the different energy scales in a system of electrons and nuclei and relate them to the relevant physical processes. Every energy scale is due to a particular type of physics, as was explained in the video. In order to help you to burning this image in your memory, I suggested that you put the a printout of this picture at a place where you see it multiple times a day, and if you want, you could send me a picture of that. And well, I show you a few pictures of these and previous years. Some people put it on the wall in perhaps their study room. Here somebody, that's really the study desk, and the picture is near to the study desk, so yes, you will see it there several times a day. There were people who put it as the background on their laptop. That's another way to see it multiple times a day. Or as an icon on the laptop. So if you click it, you immediately have the picture. That's also a possibility. In the kitchen, you see the hood above a stove in the kitchen. So sure, if you cook a lot and you put the picture there, you will see it many times a day. And this is my favorite of a few years ago. A student with a small baby. So if you put the picture next to the diaper changing table, then for sure you will see this multiple times a day. So keep this as a message. Look regularly at this picture. Try actively go through the reasoning. And after a while, this is so common knowledge, you will never forget it anymore. And this will be a very useful starting point to relate everything you see about the physics of hyperfine interactions into one scheme. Let me have a look at the chat to see whether there is no question there. So feel free to ask questions during the webinar. I will regularly go there and look what might be present. Okay, let's then go into one of these energy splittings. Not yet the hyperfine interactions, but the fine structure, the level that comes before, the level to which the hyperfine energy levels are a correction. And the fine structure splitting, that is a splitting that was due to spin-orbit coupling. So where do we have them in the picture? It's the level just before the hyperfine interactions. Typically milli-electron volts as energy splitting due to spin-orbit coupling, which is said to be a relativistic effect. And I asked you the question, why is that a relativistic effect? Because that is not necessarily obvious. And some people answered that this is due to the speed of the electrons, which is not entirely wrong, but it's not enough as an argument. So we need to be more precise. And there are actually two arguments that you can use to justify that spin-orbit coupling is a relativistic effect. The first argument is spin-orbit coupling is very much related to the spin of the electrons, and therefore, spin comes naturally from the Dirac equation. The Schrödinger equation does not have spin. You can see this in this way. If you check the Schrödinger equation, it doesn't have spin. It doesn't know about relativity, and therefore spin-orbit interaction is not present there at all. You can, however, introduce spin in the Schrödinger equation artificially. It doesn't spontaneously roll out of the reasoning, but you can modify the Schrödinger equation and put spin into there. And you can add spin-orbit coupling as a perturbation to the Schrödinger equation. So you add yourself an extra term, wherever it comes from, that describes the spin-orbit coupling in a first-order perturbation. However, if you would solve directly the Dirac equation, that one has all these ingredients naturally. There is spin, there are all relativistic effects up to all orders, and therefore also spin-orbit coupling. So fine structure being related to the spin of the electrons and spin-orbit coupling, that is a relativistic effect because it is so tightly connected to the Dirac equation. That's one argument. Another argument that several people used is spin-orbit coupling is due to an relativistic effect where indeed the electron is moving at a high speed, and at these high speeds what we call electric fields and magnetic fields, that is not the same as at low speed. In the Lorentz transformation, there is a change between what we call electric and magnetic fields. So at high speed, you can experience different effects of a magnetic origin, whereas without the high speed, there was no magnetism at all. So that too is something that is very tightly connected to spin-orbit coupling. And I have just a very visual sketch of the reasoning here. It's not a mathematical explanation, but to give with an image what it is about. If you have a train with an electrical charge in the train and a magnet, then for an observer outside the train, for an observer inside the train, there is no interaction between this charge and the magnet. An electrical charge and a magnet, they do not interact with each other. But if you are an observer outside the train and you see this train passing very fast, then that charge is a moving charge, it's a current. So that produces a magnetic field. And therefore, it should interact with the magnet. So what does it do? Does the charge interact with the magnet as the observer outside the train sees? Or does it not interact with the magnet as the observer inside the train sees? There can be only one solution, and it doesn't interact, but how is that then explained by the observer outside the train? Because part of the magnetic fields are transformed into electric fields and the other way around. And these changes to the fields, they counteract the interaction that you would expect just by considering the moving charge as a current. So both observers agree that the same happens, but they explain it in different ways. And something very similar is happening with spin-orbit coupling. There we have the electron orbiting the nucleus at a high speed. If it orbits the nucleus, there is orbital angular momentum involved. And in a classical picture, if the electron would be a planet orbiting the sun, then you can imagine that the orbital momentum vector, the orientation of that vector, that one explains something about the geometry of the orbit of the electron. If the arrow for the orbital momentum is pointing like you see it here on the screen, then you know the plane in which the electron is moving in a classical sense. But in a quantum picture that remains roughly true. The orbital angular momentum tells something about the localization in space of the electron. An s orbital will look differently from a p orbital. The electron also has spin, intrinsic spin, so it acts as a bar magnet. It generates a magnetic field, and that magnetic field that can interact with the nucleus, with the spin of the nucleus. And what we are asking in spin-orbit interaction, in spin-orbit coupling is, how is that orientation of the spin of the electron? How is the bar magnet of the electron oriented with respect to the orbit of the electron? In a classical picture, is it perpendicular in the positive direction to the orbit? Does it lie in the plane of the orbit, or is it oriented anti-parallel to the orbit? And that is what the total angular momentum J expresses. If J is maximal, then the orbital angular momentum L and the spin angular momentum S are parallel to each other. If J is minimal, they are anti-parallel. If J is 0, they are perpendicular to each other. So this image here, this cartoon, tells visually what spin-orbit coupling is about. And that is a relativistic effect, because that fastly orbiting electron, what you call electric fields due to the charge of the electron, current due to the motion of the electron, and magnetic fields due to the spin of the electron, all these effects are transformed by the Lorentz equations because that electron is moving that fast. So finding how large exactly the spin-orbit coupling is, that is not possible in a classical picture. You can get the meaning of the concept as you see here, but if you make a fully exact classical calculation of the effect, it will not be sufficiently large. It's heavily modified due to the Lorentz transformations. The way how spin-orbit coupling is often visually explained is you start at, you sit yourself at the position of the electron, and seen from the position of the electron, the nucleus is now orbiting the electron. Just as seen from the position of the Earth, it looks like the Sun is orbiting the Earth. 24 hours are needed for a complete revolution. Well, an observer at the electron experiences the same. And it's this orbital current of the moving nucleus that creates a magnetic field at the center of the electron, and that magnetic field interacts with the bar magnet of the electron. It tries to orient the bar magnet. That is another picture to explain spin-orbit coupling. So you have this orbiting nucleus, the current. The current needs to be large in order for the effect to be large. That means the electron should move at a high speed, then also the nucleus will move at a high speed seen from the position of the electron. Where do you have the highest speeds? That is in the heaviest atoms. So you can expect that spin-orbit coupling will be most important in the heaviest atoms. And you need, of course, spin as a prerequisite. If there is no spin, if there would not be spin on the electron, then there would also not be spin-orbit coupling. Before moving on, let me look at the chat. Nothing there. Then to illustrate fine structure, again, not the topic of this course as a whole, but the starting point where we will apply the hyperfine interaction. So it's nevertheless important to have a good picture what the fine structure is. So therefore, in order to illustrate the fine structure, I invited you to look at the 3p to 3s transition in sodium, which is a technologically relevant phenomenon. And I asked you to search some explanations about it. I just copied 2 of these explanations here on the screen. You can later make a screenshot out of this or go back to the video and read it carefully if you want so. but these are textbook explanations of what that transition is about. And graphically and visually, you can picture it in this way. You have at the bottom the ground state of the sodium atom, then two excited states. If the atom goes from these excited states back to the ground state, then a photon is emitted, and because there are two excited states close to each other that are a few millieV apart from each other, well, therefore you have two transitions that are very close together. So if you would take a spectrogram, as you see on the left-hand side, you would see that you have not one line, but indeed two lines. And the fact that you have two lines, that is a fine structure splitting of that excited state due to spin-orbit coupling. How can we write that down? How can we characterize this splitting, and how can we connect that to that total angular momentum J? Well, that is related to the term symbols. And what we will try to understand in the next few slides is, can we see whether that lower of the two levels, how is it characterized, what are its quantum numbers, and to which of these three situations does it correspond? Is the electron spin parallel, antiparallel, or perpendicular to the orbital angular momentum? And in order to do that, you need to understand term symbols for free atoms. Another topic that is not part of this course, something you very likely have seen before, but we need to understand this very well in order to work with it. It will be important. The same reasoning as for term symbols will be important for, in the first place, magnetic hyperfine interactions as well. So let's revisit term symbols. Let's apply that to sodium, an atom from the first group of the periodic table, so one electron in an s orbital in its ground state. And let's try to write down the term symbol for that ground state and for these excited states. Here you have the general notation for the term symbol. And first of all, we need to find what is the capital S for an atom. This is a sum over the ms values of the electrons. There is only one electron, so we have only one ms, being 1/2. So twice 1/2 plus 1, that's 2. So as long as you have just one electron outside the noble gas core of sodium, you will have, in this superscript, you will have 2. The X, that is the capital L, and that's a sum over the ML, the orbital angular momentum quantum number for every individual electron. So you make the sum over all of these. If that total L turns out to be 0, you note X as S. If it turns out to be 1, you note X as P, and so on. For our ground state, there the electron is an S electron, so its ML is 0. There is only one ML, so the total L is also 0. So there we would have an S. If that single electron is excited to the p orbital, then its ML is 1. And that can be 1, 0 or minus 1. We have only one electron, so the ML in absolute value must be 1. If you sum over them, it's p. So it's the total L is 1, so we denote this as p. And then the last one, here we come to spin-orbit coupling. The J is the relation between our L and S. If j is minimal, then its value is the absolute value of L minus S. If j is maximal, it's L plus S. And depending of whether a shell is more than half filled or less than half filled, either the L minus S or the L plus S is the lowest energy state. These are Hund's rules that can guide you through predicting what are the lowest lying states in excited atoms. Well, if you apply this to our sodium atom, then I said the 2s plus 1 will always be 2. That you see indeed for all of these three levels, that's 2. In the ground state, our total L was 0, so that's a capital S. In the excited state, the total L is 1, that's a capital P. Then for the ground state, what is J? We have either L minus S, so 0 minus 2 absolute value, that's 2, or 0 plus 2, that's also, what am I doing here? No, sorry, erase, go back 30 seconds, no, I don't have my pen here, so I cannot write it on the screen right now. That would have been better. For the ground state, the S is 1/2. You write it as 2, but that is because S is 1/2. The L is 0, so we have 0 and 1/2. You can go from L minus S absolute value, that's 1/2, to L plus S, that's also 1/2, so there is no discussion, J is 1/2. For the excited state, we still have S 1/2, but now L equals 1. So we can go from L minus S, that's 1/2, to L plus S, that's 3/2. And there are only two possibilities here, because the difference between them is 1, and you go always in steps of 1, so only two possibilities. And these are our two spin-orbit split levels. Depending on the value of J, there are only two values of J here, you have different levels. Which one is lowest in energy? Apply Hund's rules. For a shell that is less than half filled, and 1 electron in a p orbital, that's definitely less than half filled. For a shell that is less than half filled, it's the minimal J that has the lowest energy. So therefore, L and S are anti-parallel in the lowest excited state. And that answers the question from which we started. It's situation C, where the L and S are anti-parallel, that is the lowest energy solution. And you can get that from Hund's rules from the term symbols. And some more visual illustrations. That's another picture of these two spin-orbit split lines in sodium. There is a typical experiment where you take a pickled cucumber, which has a lot of vinegar inside, and if you put a high voltage on this cucumber, then you can excite the sodium atoms in the vinegar, and when they fall back to the ground state, you have this orange light coming from your cucumber. Another place where you used to see it in the past, but this is rapidly going away now, at least in this place in Europe. You had the sodium lamps in highways, in streets, which that typical orange light that you saw in all the previous pictures. Yeah, they are being replaced by LED lights now, so which is more like daylight, and this orange glow with a lot of these photons that were fine structure split, and that is disappearing. Back to the chat. No questions there. Then we move on to the gravitational analog, which some people liked and other people had some doubts or questions about. So what is the point? We have a situation with two mass distributions, two deliberately general mass distributions. They are not moving. We take a static approach, so they are fixed in space, but we examine what is the potential energy, the gravitational potential energy of this system, and therefore, if these mass distributions would be free to not move, but at least to rotate, how would be the orientation they take in order to be in the lowest energy situation? And that is something in classical physics you can easily write down. That potential energy is the integral of the mass distribution of one of these mass distributions times the potential, the gravitational potential generated by the other mass distribution at every point inside the first mass distribution. And this you integrate over the first mass distribution and you get that potential energy. And this is something you can write more explicitly. You have the expression for the potential of the second mass distribution. You can fill that out in the expression for the potential energy, and you found that this potential energy is this double integral over the two mass distributions as written there in the red box. Now, this was told from the point of view of mass distribution 1. And just as we made the transition in the spin-orbit coupling story of being an observer at the nucleus to being an observer at the electron, so we switched the point of view, well, also here you are free to switch the point of view. You could ask, what is the potential energy if you reason from the point of view of mass distribution 2? And I asked you, verify that this doesn't matter, that you find the same potential energy. And here is one of your answers, so you see the same 3 steps, and no surprise, that gives exactly the same expression. At least if the order of integration would be if you could change the order of the integration, and for well-behaved mathematical functions like these mass distributions, that will be the case. I have another very simple but illustrative analog to this. If you would have a classical hydrogen atom, so a positive charge and a classical negative charge that is on an, say, circular orbit, how would you write the potential energy of that system? Well, you could reason, I take the charge of the electron, minus Q, and I multiply it with the potential, the electric potential due to the nucleus at the position of the electron. And that is, apart from some constants, the charge of the nucleus over the distance, which is here r for this hypothetical circular motion. So the energy of the entire system, the potential energy of that classical hydrogen atom would be minus Q times Q over R, a charge times a potential. However, you could imagine this from the position of the electron, from the position of the nucleus. You could also sit at the position of the nucleus where you have a charge Q and look at the potential generated by the electrons at the position of the nucleus. And that would be minus Q over R. So it's exactly the same result, but the way how you write it, either from the point of view of the electrons or from the point of view of the nucleus, the way how you write it is different. And historically, traditionally, if you reason about energies in atoms, we take the point of view of the electrons. We always say it's the electron that is our starting point, that moves into an electromagnetic potential created by the nucleus, and we solve the system from that point of view. In hyperfine interactions, it's much more natural to take the opposite position and to reason from the point of view of the nucleus. So we sit at the nucleus, we know the properties of the nucleus, and then the electron cloud that surrounds us creates all kinds of electromagnetic fields at the position of the nucleus, and we observe how the nucleus reacts on these electromagnetic fields. So it's a mental switch you have to make to think about energies of atoms, molecules, crystals, not from the point of view of the electron cloud, but from the point of view of the nucleus. That doesn't change anything about these energy levels themselves. That these energy levels and the distances between these energy levels, that does not depend on the point of view. But the way how you reason about it, what you take as a field or as a potential and what you take as, say, a charge, the point of view from which you think, that differs. So try to make that mental switch. From now on, we think from the point of view of the nucleus. We are an observer at the nucleus. Several people made the comment that they do not get what this gravitational analog has to do with the story I just told, or with the story of hyperfine interactions in general. And here, and also in a few minutes at another point, I want therefore to emphasize the correlation. One of our mass distributions will be the nucleus, and we will reason from the point of view of that nucleus. Our second mass distribution, that's the electron cloud, and that is a generator of fields or potentials. And we will look how mass distribution 1 should orient itself in order to lower the energy of these two gravitationally interacting mass distributions. There will be the example with the double ring where this point can be made very clearly. So I will come back again to that same statement when we will discuss the double ring. If we then try to solve that double integral, which is for general mass distributions a very complicated solution, well, then we realized we can make a series expansion of this and therefore approximate the result in a numerical way. And in order to make that series expansion, there was this condition r smaller than r prime. The nuclear coordinates, the lengths of the position vectors inside the nuclear volume, are they always smaller than the length of the position vectors inside the electron cloud? If that is true, if one is always smaller than the other, then our series expansion becomes a bit simpler. This series expansion, this very general Laplace expansion, if that condition is fulfilled, then it separates into an series of dot products between tensors of increasing ranks, but one tensor only depends on nuclear properties, the other tensor only depends on electron properties, and you have in every term a dot product between something nuclear and something electronic. If that condition is not fulfilled, then this clean separation is not true anymore, and you have extra terms to take into account. In case you wonder about this very exact formulation of the Laplace expansion, I can refer to Wikipedia, where they have this expansion discussed in the most general case with indeed an r smaller than and an r larger than. If you understood this, then you can answer positively to the confidence statement, I can write down an expression for the gravitational potential energy of two interacting mass distributions, and I can explain why a multipole expansion of this expression is convenient. So why is it convenient? Because it's a way to solve that complex double integral. If your shape of your mass distributions is very general, then by looking at the highest order terms in this multipole expansion, you at least have the major contributions to the energy. And another confidence statement, I can explain the issue of these r smaller than and r larger than when what would be simpler, of what would be the consequences if that condition is fulfilled, and what could be situations where the conditions are not fulfilled. And that is something I asked you explicitly. I asked you to draw some examples of classical mass distributions where that condition is not fulfilled. And I show here a few examples of previous years and most of them of this year. Examples you have submitted as answer on that question. And there are a few here that are not correct. So in the right hand side you have your position vectors that start from two different origins, and that's not something, that's not correct. We have the origin of our axis system, and all position vectors start from there. And at the left-hand side, we always made the convention that we put the origin of the axis system in the center of mass distribution 1. So if you don't follow that convention, then indeed the lengths of r and r prime can be anything. And I will try to close the door here because there is some noise going on outside. Yeah. So these are solutions that are, or answers that are not correct. Some people tried things like this, two mass distributions that overlap in the sense, they are really, there are positions in space where you are inside the two mass distributions simultaneously. That is of course not easily possible because two objects cannot occupy the same place. But if you consider this as a 3D example where you have two very flat mass distributions and you put one on top of the other, then these solutions could be correct. Then you could have indeed in this way situations where the condition is not fulfilled. There are other examples of this here. Then there are solutions where you kind of reverse the roles. Rather than having mass distribution 1, which will mimic the nucleus, being surrounded by mass distribution 2, which mimics the electrons, you could switch the roles and have electrons surrounded by a nucleus. And then, of course, you also have a violation of this condition. A more realistic, at least for nuclei, for atoms, a more realistic situation would be what I call the bulges. So if you have a part of the electron distribution that is entering the region where you have mainly the nuclear distribution, like, and I will use the pointer, like in this situation here, blue is the nuclear mass distribution and red is the electron cloud. Well, if part of the electron cloud would be present here, then very clearly you can have position vectors in the electron cloud that have a length shorter than position vectors in the nuclear part. And all of the examples you see here, they are in one way or another realizations of such bulges. You can also make long and flat mass distributions. Many examples are shown here. And also in these cases, the condition can be violated. And some people have some sometimes very ingenious 3D solutions. Also this year, the picture here was from somebody of this year who has some drawing talent and who sketched two mass distributions that make a very organic, natural shape, and in which this condition is not fulfilled. There is one example I show every year, and which I call the all-time winner, of a very simple but very clear illustration of violating this condition. And that's this example. You have mass distribution mass distribution 1, which would be the nucleus, is here a ring, and mass distribution 2, the electron clouds, is a rod. The rod is penetrating the inner part of the ring, and also here this condition is not fulfilled. And that's an important insight. So for atoms, for nuclei and electron clouds, it looks very natural that this condition is fulfilled. And we might be inclined to think that condition is simply true, and we will have this clean separation in nuclear tensors and electron tensors. But it's not very exotic to think about situations where that condition is not true. If you would apply this to problems in classical mechanics or problems in cosmology, you could imagine two galaxies of shapes like the one you have in this example, and these galaxies are going through each other, and you want to find the gravitational potential energy represented by the current position of these two galaxies. Well, you could easily run into situations like this one, where that condition is not fulfilled. So, although the Laplace expansion with that r smaller than and r larger than symbol can look like a weird thing, we really need it. There are situations that are not exotic, like the one you see here, where the full details of that expansion are really needed. You might think, not for atoms, not for nuclei and electrons. And yes, the major part of the interaction between nuclei and electrons are not affected by this are smaller than or are larger than. However, it does happen. This you will see from next week onwards, that this condition, even in atoms, is not fulfilled. It's only slightly violated, but it is violated, and that will give rise to extra terms where these electronic and nuclear tensors are mixed, and that will give extra energy contributions, one of them being an example of a hyperfine contribution. So that was a long story about this Laplace expansion. I go back to the chat, nothing there. Then let's try to train our calculation skills a bit, not just for fun, but because this can help contributing to our insight in what was asked here, the monopole moment, a topic of last week, and the mean square radius, a topic, a property that will be important in the week that comes. And I asked you calculate for these 3 charge distributions, 2 discrete and 1 continuous one, what is the monopole moment and what is the mean square radius. And well, you didn't need to do the mean square radius for the cube, because that is mathematically a bit more involved, but it should be rather straightforward for the 2 discrete mass distributions. And well, the monopole moment, that was trivial, that was just recalling what you did last week. Monopole moment is the total charge, so therefore just sum the charges and that's what you get. And in all 3 cases it was said that you have a total charge Q that is distributed in 3 different ways, so therefore the monopole moment is simply Q. And one of you wrote, I think I oversimplify it, but no, you do not oversimplify it, it's just Q. So if you understood this, if you didn't search any further and were happy with the simple answer, well, that's an indication that you understood what the monopole moment is. But the main part of this exercise was about this mean square radius, and that expresses, if you would have to approximate this charge distribution by a sphere, what would be the average radius, what would be the radius of that sphere, the radius of a sphere that approximates this particular mass distribution, and not the radius as such, but the square of the radius. Here I show 2 examples, a typed one and a handwritten one, where for the first case the correct solution is found. So the mean square radius is the distance between the 2 charges squared divided by 4, which would mean that the radius of that sphere is the distance between the 2 charges over 2, which is not if you would intuitively have to draw such a sphere, you would probably have drawn something very similar to that one. Some people hesitated about the definition of the mean square radius. So the exact mathematical definition is you take the continuous charge distribution or mass distribution, rho of r, you multiply it in every point of space with r squared, you integrate this over the entire volume of the mass distribution, and you divide by the total mass, so the integral of the mass distribution itself. And if this is a discrete situation, if you have point masses or point charges, then these integrals turn into sums, and you have what is here at the right hand side. Keep in mind that the answer for the mean square radius depends on the origin of the axis system. So if you take the origin of the axis system as in the left hand side, in one of the particles, or at the right hand side in the middle of the particles, then you get a different answer. Is that something that will bother us? Not too much, because the mean square radius will be a property of the nucleus. We think from the point of view of the nucleus. We have the convention that we put the origin of our axis system in the center of charge of the nucleus, and therefore, yeah, it's natural to have something like on the right hand side. Also there, the origin of the axis system is in the center of charge of the 2 point charges. So that will be the natural answer for our nucleus. And it becomes a bit more complicated and a bit more interesting in the triangle, so that's a less trivial case. So also there if we follow our convention, we take the center of mass or the center of charge as the origin of the axis system, and it's in this axis system with this origin that we express our mean square radius, and we will find then a squared over 3. And also here, not surprisingly, if you take the square root of this, then you have a over square root of 3, and that's the distance that is flashing there. So if you would make a sphere that has as radius the root of the square root of the mean square radius, then you would have a sphere that goes through all of these 3 particles. So the idea of a mean square radius is agreeing with our intuition, I would say. This is the explicit calculation for the 2 previous cases. So if you want to verify your own results in case you found something different, but most people found the correct answer. So if you want to verify your own result, you can do it this way. And the last one, the continuous charge distribution, the cube, if you are interested in the result of that one, so here is a short version of the solution of this one. So a squared over 4, the same as for the 2 charges, the 2 point charges, that would be the mean square radius here. Nothing in the chat. I continue. I asked you then to show an example of a situation where you used previously in your education a principal axis system, because a principal axis system is something we will need here. It's a special choice of axis system in a way that makes the tensor of properties that we are examining as simple as possible, with as many zeros as possible. That's the meaning of as simple as possible. We will see explicit examples of this, both for the magnetic hyperfine interaction and for the electric quadrupole interaction, in 2 different ways how to find a 2 different illustrations of the concept of a principal axis system. But here at this point we are satisfied just with the general idea, as many zeros as possible. And in order to draw your attention to the fact that this is not something new, that this is something you have used before, I asked this question. And several answers to this. Some people have met it in mathematics, diagonalizing matrices. That is essentially finding a principal access system, finding an access system in which you can write that matrix in a way that is as simple as possible. And the same idea, but in a different wording. And what was the wording again? Yeah, moments of inertia. They are matrices, or you could write these as matrices. And if you choose an access system in which the moments of inertia are simplest, are diagonal matrices, well, that boils down to rotating your access system in such a way that the moment of inertia, the tensor that you are examining, that this has as many zeros as possible. So you can look at this as a mathematical thing or as a physics thing. With moments of inertia, you do this for a physical system. There are more examples of this soon. Yeah, here you have them. Many people mentioned the the problem of someone called it the Euler-Poisson problem. I didn't know the terminology actually. I had to look that up, but that's apparently a general name for the motion of a rigid body, not necessarily actually symmetric, that can freely rotate. So the top problem, the problem of a rotating top, where the top even can be not actually symmetric. Many physics students have gone through a solution of that problem. It's a very typical one in classical mechanics. And yeah, definitely you will use a principal access system there, because your properties and your solutions will look most simple in that principal access system. Some people referred to engineering courses. Courses, well, in the context of construction engineering, if you have an object, say a beam, and you want to analyze the strains and stresses in that beam, then the simplest description of this is if you do this in the principal access system. So you have a strain tensor or a stress tensor. Again, we have tensors, and they become most simple in their principal access system. In crystallography, you have similar things. Some people mentioned explicitly crystals, and even in optics, and somebody mentioned light propagation in birefringent media. So also there, if you describe that in the principal access system that is relevant there, then your property is expressed in the most simple way. So principal access systems are not new. That's the message behind this. Then we come to an explicit realization of our gravitational example, the double ring. And again, here the question was raised by some people: how does that relate to atoms, to nuclei and electrons? And well, let's explicitly look at that double ring. So don't look at the question yet, but at the double ring system. So what do we have in the double ring? We had a mass distribution here in the center of the axis system that is not drawn on that picture here. That mass distribution was a dumbbell. And we have a mass distribution that is drawn here, and these are these two rings. You could imagine that the dumbbell is a representation of the nucleus. So an object, a mass distribution, but for the nucleus it will be a charge distribution with a particular geometrical shape. It's not a point, it's even not a sphere, it's something more complex, it's a dumbbell. And we have an electron cloud, these are the two rings, that are not necessarily spherical. So two rings, that's not a spherical electron cloud. Both of these objects are fixed in space. They cannot collapse, they cannot go to each other. But my nucleus, my dumbbell, is assumed to be free to rotate, and it can adopt an orientation where it minimizes the energy of this system. When stated in this way, in a gravitational context, and with these simple mass distributions, this is something you can even solve analytically. But we don't do that. We say, okay, let's apply the multipole expansion to this. And let's see what is the monopole term, what is the next non-zero term, the quadrupole term. And this quadrupole term, that is listed here. So you have a dot product between two tensors of rank 2. And a dot product is a number, one number, and that number depends on a factor that contains geometrical information, the two masses, the length of the dumbbell, the distance between the rings, the radius of each of the rings. So all of these geometrical properties combine into this factor alpha, and then a term that depends on the angle theta, which is the angle that gives the deviation of the dumbbell orientation with respect to the vertical axis. And this is an actually symmetric problem, so theta describes everything. The angle phi that gives the orientation in the xy plane does not play a role here. That orientation does not matter, it doesn't affect the energy. So with this problem, with this simple problem, if we calculate the quadrupole term, we can try to intuitively verify whether that calculation makes sense. And that is what I asked you. I asked you, look at this problem just visually and try to reason what would be the lowest energy orientation of the dumbbell in each of the three cases that are shown here. The rings very far away from each other, that's the left hand side. The rings very close to each other, that's the right hand side. And then a particular situation in between that has the property where this factor alpha is 0. And that is a particular arrangement. Well, we will come to that when we will study the field gradient tensor. You will understand what is special about this arrangement. So, but take the left-hand side and right-hand side example and try to reason what the dumbbell will do. If you take the left-hand side, the rings are very far away from each other. In the limit of almost infinite distances, it would be as if the rings would be two point masses. And the dumbbell, how will the dumbbell, if it is attracted by the point masses, gravitational interaction, how will it minimize its energy? By aligning with the z-axis, because then each mass of the dumbbell is as close as possible to another mass. If, however, the two rings would be very close to each other and be even in the limit coincide in the same place, How can then the dumbbell minimizes its distance? By being in the plane as well. So a dumbbell perpendicular to the z-axis in the right hand case and a dumbbell parallel to the z-axis in the left hand case. That would be the intuitive solution, and that is also found if you look at the explicit term of the quadrupole interaction, the quadrupole energy. If you would make the analytical solution of this double ring system, then you would of course also find the same result. But the message here is already after the quadrupole term, the right physics of this problem is recovered. The monopole term, that is not sufficient. There you have an answer that is orientation independent. In the monopole term, my nucleus is not a dumbbell but a point, and a point can have no orientation. It's only in the quadrupole term that orientation appears, and that is the leading term where we will see all these orientation effects. If we will ask for hyperfine interactions, what is the preferred orientation of the nucleus in a magnetic field of the electron cloud, in an electric field gradient of the electron cloud? Well, then we need these we need these multiple terms. We cannot stick to the zeroth order where we just have a point nucleus. So if you wonder what is the reason of this gravitational example, it's an illustration of the concept of the multipole expansion in a situation that is simple enough such that you can explicitly verify everything mathematically, and that is intuitive enough where you can even reason about it without using mathematics. Okay, and here I have everything set that is on this page. Yeah. Okay, and so the confidence question, the confidence question checks whether you see the connection between this gravitational example and the real atom. The last part that we have to do, and I look again at the chat, nothing there. The last part we have to do is the quantum multipole expansion, and that is now this is now this is combining the idea of the multipole expansion with quantum physics. And I asked you, describe the complications you would run into if you would try to use perturbation theory to study a system with a nucleus of a general shape without having made first a multipole expansion. And I draw there a nucleus with a very general shape. So you know the point nucleus result. That is what you have studied in atomic physics so far. And now I want to have a nucleus with a complicated shape. So I add that complication in perturbation theory. Well, what is the complication you would run into? Your perturbation is very complicated. Your small effect that you add is very difficult to solve. And that is where the multipole expansion enters. If we could approximate our complicated nucleus first by a point, that we have already done, but then by something with some volume, with some shape, so much simpler terms, much simpler shapes that catch at least the most important effects of the total shape of the nucleus. Well, if we would use these in perturbation theory, these perturbation terms would be easier to solve. So that is the idea of combining perturbation theory, which is a typical method in quantum physics to study something that is a bit more complicated than what you already solved before. And combine perturbation theory with the multipole expansion, because the multipole expansion allows us to isolate the leading terms that go beyond what we already know, that go beyond the point nucleus. And okay, I see that we are already running late. We should basically finish here. But the last part was verifying that the reasons why it is allowed to use perturbation theory and the reasons why the multipole expansion is rapidly converging and such, and therefore that we can use only the leading terms, that these two reasons are, or these two conditions are simultaneously satisfied. So for the multipole expansion, and that will converge fast if the typical distances in the nuclear charge distribution are much smaller than the typical distances in the electron cloud, which is obviously true. And the first order perturbation theory, that one will be sorry, I try to hurry up and then of course I get confused. So this is the expression of first and second order perturbation theory, and I lost the point here, so we should see from this that first order perturbation theory is much more important than second order perturbation theory for the same reason as for the multipole expansion, namely nuclear coordinates much smaller than electron coordinates. And I don't see the point right now. So I promise next week I will come back to this and I will recover what I was thinking. I'm going nuts here. But in general, the summary of this part is, if you have a classical system like our gravitational example, and you want to make that mathematically tractable, then you use the multipole expansion, nothing more. If you have a complicated quantum system and you want to treat that mathematically in a tractable way, then you have the multipole expansion, but combined with perturbation theory. So you need two ingredients rather than only one in a classical system. And everything that we will see with hyperfine interactions will be make a multipole expansion of some Hamiltonian and use that in first order perturbation theory on top of the point nucleus. That idea will come back several times. Good, sorry for being a bit later than usual, and sorry for missing the point there at the very end. Are there any further questions? So it has been silent on the chat, but that doesn't mean that you cannot ask questions now, so I will wait for another 30 seconds or so. And if there are no questions appearing by then we will finish here. don't see any. So then we'll see each other next week, and very likely that one will be pre-recorded because I will not be at the usual place on Wednesday morning. So, but I will pre-record it on Tuesday evening, and it will be streamed automatically on Wednesday at the usual time. So, see you next week for the first real hyperfine interaction. Bye bye.